We often hear that nothing can travel faster than the speed of light. This is one of the most fundamental principles in physics, a cornerstone of Einstein's theory of relativity. In the vacuum of space, light zips along at an astonishing 299,792,458 meters per second. This speed, often denoted by the letter c, is the ultimate cosmic speed limit. No object with mass can ever reach this speed, let alone exceed it. It's a barrier that seems absolute and unbreakable. But what happens when light isn't in a vacuum? Does its speed remain constant, or can it change? When light travels through a material like water, glass, or air, it interacts with the atoms and molecules within that substance. These interactions cause the light to slow down. It's not that the individual photons themselves slow down, but rather the light wave's overall progress is impeded as it's absorbed and re-emitted by the particles in the medium. Think of it like running through a crowded room versus running in an open field. You're still running, but your effective speed across the room is much slower due to the obstacles. In water, light travels at about 75% of its speed in a vacuum. In glass, it's even slower, around 66%. The speed of light is context dependent. Now, here's where things get truly fascinating and seem to challenge that universal speed limit we discussed earlier. While nothing can exceed the speed of light in a vacuum, it is absolutely possible for particles to travel faster than the speed of light in a specific medium. Consider a high-energy charged particle, like an electron or a proton, moving through water. If this particle is accelerated to a very high speed, it can actually move faster than the speed at which light travels through that water. This isn't science fiction, it's a real physical phenomenon. The particle is not breaking the universal speed limit c, but it is exceeding the local speed of light in that particular material. When a charged particle travels through a medium faster than the local speed of light in that medium, something remarkable happens. The particle disturbs the electromagnetic field of the medium, much like a boat creates a wake as it moves through water. This disturbance propagates outwards as electromagnetic radiation, specifically light. But because the source particle is moving faster than the waves it's creating, these waves pile up, forming a cone of light. This is analogous to how a supersonic jet creates a sonic boom when it breaks the sound barrier. The sound waves pile up, creating a shock wave. The light emitted by this process is known as Cherenkov radiation, named after Soviet physicist Pavel Cherenkov, who first characterized it. This radiation is typically emitted in the ultraviolet and blue parts of the spectrum, which is why it often appears as a distinctive blue glow. It's a continuous spectrum, unlike the discrete lines seen in atomic emissions. The blue color is simply the most visible part of the spectrum for the human eye. This eerie blue light is a direct visual signature of particles exceeding the local speed of light. The most famous place to see Cherenkov radiation is in nuclear reactors. The fuel rods are submerged in water, which acts as a coolant and a radiation shield. High-energy electrons and other charged particles are produced during nuclear fission. These particles travel through the water at speeds exceeding the speed of light in water. The result is the iconic, intense blue glow emanating from the reactor core, a visual testament to this intriguing physical effect. Cherenkov radiation is also used in particle physics experiments to detect and identify high-energy charged particles. Specialized detectors capture this light to track particle paths and measure their speeds. So, while the speed of light in a vacuum remains the ultimate speed limit for anything with mass, the speed of light in a material is slower. And in that slower environment, charged particles can indeed outrun the light waves they generate. This doesn't violate the fundamental laws of physics, it simply highlights that the speed of light isn't a single, fixed value in all circumstances. Context matters. The medium through which light travels fundamentally affects its speed. The blue glow of Cherenkov radiation is a beautiful and powerful reminder that even in the seemingly absolute rules of physics, there are nuances and phenomena that continue to intrigue and educate us. It's real physics, not science fiction, and it's happening right here on Earth.